We're going to look at this thing called the primitive function. Basically, solving this sort of thing. Say we're going back the other way. We know the equation of the tangent, but it's the equation of the original curve we want to find. So going back the other way. Talk about polynomials to start off with, because polynomials, as I've mentioned before, are very important because all of our different functions we could rewrite as an infinite polynomial. So if we know how to do it to polynomials, theoretically we should then be able to do it for any function we like. Why is it called the primitive function? Well, because we're just going back to the start. We know that when we differentiate a polynomial, we take one off the power. So logically, to go back the other way, we would add one to the power to get back to it. We also know that when we differentiate, we would multiply by the power. Now, if we're going back the other way, we'll divide by the power. So basically, x to the power of n, add 1 to the power over to that new power. So x to the power of n over n plus 1. Something like this. We know the derivative is 3x to the power of 4. So f dash x is our derivative. We want to find the original function. Well, we add 1 to the power, 5, over the power 5. But the thing is with the primitive function, we need to add a constant, because if you recall, when you differentiate a constant, you get 0. So in going back the other way, it's quite possible there might have been a constant there. And then when we differentiated it, it became 0. So how do we know? Well, we don't. Best we can do is simply say, look, it's going to be plus some constant number. Now, it might be that that constant number is 0. It's still a constant number. But unless they give me more information, I can't do any better than that. So just plus some constant number. If we have more than one term, just like when we're differentiating, we just do each piece individually. So 6x to the cube, add 1 to the power, becomes 4 over 4. 5x squared, add 1 to the power, becomes 3 over 3. X to the power of 1, well, becomes x squared over 2. That constant 2, which theoretically is 2x to the power of 0, theoretically, add 1 to the power, 2x. And again, it could be plus some constant number. Well, that tidies up. 6 over 4 is 3 on 2, isn't it? Yeah, that would have been the original function. What we're actually doing, basically, is finding a family of functions. Because remember the effect the plus the constant has on your graph. It just shifts the curve up or down. Well, if all we're doing is shifting the curve up or down, well, the slope of the tangent at any x value will stay the same. It's just being moved up or down. Remember, the derivative doesn't tell you the equation of that tangent, it tells you the slope of it. So moving it up or down is not going to change it. So again, another reason why we have plus a constant. Let's do one where we do have extra information. So there's this whole family of curves. We want the specific one that will go through the point 1, 1. So only one of them will go through 1, 1. We know it has a gradient function of 2x plus 3. Gradient function, that's just another way of saying the derivative. So remember, the derivative is the function that finds the gradient. So you can sometimes see it called the gradient function. Okay, my derivative, I'm going to call it dy dx this time because I want to end up with an equation y equals something. Makes sense to use that. 2x plus 3, add 1 to the power over the power. So the 2x becomes x squared, the 3 becomes 3x, plus some constant. That tells us the family of functions, all the different ones we could possibly have. We want the specific one, that when x equals 1, y also equals 1. We just substitute in, rearrange it, and we can find what our constant is. So it must have been -3 for this to work. Therefore, the original curve was y equals x squared plus 3x minus 3. 4j. A nice quick one today.